Welcome. In this video, we discuss first-order linear differential equations, but this time with non-constant coefficients. That means we will look at a differential equation where the coefficients are functions of the independent variable x, rather than constants. Let's get started. So I write down a general linear differential equation of first order, but the coefficient here depends on the independent variable x, now a of x, and some non-homogeneous term f of x. Look here, without loss of generality, here is a 1, a coefficient is 1. As we can divide, if there would be a function, we can divide by this here and set this form. So we only need to study that form here. F of x was also called forcing function, and what is given in our case is the a, and also the forcing function they are given, and we want to compute the solution y of x of this system. You might know that the solution consists of two parts, the homogeneous and the particular solution. So let's get started with the homogeneous solution. We follow the usual procedure. So homogeneous solution means this is equated to 0. But you cannot use the characteristic polynomial now because this was only possible, applicable for constant coefficient linear differential equations. So you need to solve this as a separable differential equation. So dy dx, you move this to the right side, yeah, is minus a depending on x times y. We omit the dependency in the y variable, that it is simply visible here for the separation. So the separation is like that. The y variables on the left side and the x variables on the right side. And we integrate this equation. The minus can be kept outside. Should look a bit nicer. We integrate the left side, which is the ln of the absolute value of y, and we do not have this a function available here specifically, so we just represent it as the antiderivative uppercase a, plus don't forget the integration constant, which can be freely chosen, of the set R. The inverse of the ln is the exponential function, plus c1 in the exponent. And now we use the power rule to split the exponent. And we know that the last part here is greater than 0, and we define it as another constant c2. Getting rid of this absolute value yields plus minus on the right side, c2 e power minus a of x, and we redefine this as a constant c, which is now a real number again because we have positive and negative constants, and also it includes 0, which is the trivial case, the non-interesting trivial case, always solving the homogeneous solution of this type. So what does it mean? That y of x, our homogeneous solution, is c times e power minus antiderivative of this given function y of x. Second part is to find the particular solution of this non-constant coefficient differential equation. We start with a proper ansatz function, which is in this case not available because we don't know what is fx, so the only solution method we can use is the variation of parameters method. So I use the same as the homogeneous solution, but I vary the constant, and this becomes a function, c of x. The rest is the same. So we need in this method also the first derivative. We can prepare it using the product rule. So derive the first factor, copy the second factor, copy the first factor, derive the second factor, and here you have the inner derivative, which is in this case minus a prime of x. And this we can further simplify, because if you derive the antiderivative, this means this will become minus small a, the original given function a of x. So we require a condition in order to get the constant function c of x, and we plug it into the differential equation here. So y prime we can simply copy. If you want to save time, you can also omit the dependency on x for all these variables, but I write it now. So this is the first derivative, and then plus a of x times the original function yp, which is short in this case. And this is gonna be f of x if it should solve the differential equation. So what do you observe here? Fortunately, otherwise there is an error. This cancels out. And we have one equation for c prime of x. So the c prime of x is equal f of x times this e power function. If you move it to the right side, the minus in the exponent changes into plus. And what does that mean? What is my c of x? It's the integration. You know, in the variation of parameters method, the crucial step is always to integrate these derivatives of constant functions, dx. Fine. Third step. The general solution is the homogeneous one plus the particular solution. So we require the particular solution ansatz, its corresponding constant, and then the summation. So let's look at an example. So the first order differential equation, which is linear, you see it here, but there is a non-constant coefficient, so we divide by x here, is the right hand side cosine of x. And we want to solve this. So we can use the algorithm, what we have studied now. So first you determine the function small a of x, which is in our case simply 1 over x. You find the antiderivative, so you need to integrate it, which is the ln of x. We avoid to write here absolute values because we assume that x is larger than 0 here. So my homogeneous solution, continue here. What is my homogeneous solution here? Probably it would be also good if we write here homogeneous subscript h. So my homogeneous solution is constant times e power minus this uppercase a function, so ln of x. And you can simplify it a little. So this is c times 1 over e power ln x to get rid of the minus, and then e power ln cancels out to just x. So we have c times 1 divided by x. So this essentially was the first part. Now the second part here. We need to figure out what is the particular solution, and we can directly start with c of x formula, which is the integration of f of x times e power ax. So f of x in our case is the cosine of x times e power, and the capital A is ln x dx. So the ln x, e power ln x, simplifies to x once again. So now you can use integration by parts. I will not show the details here, you can practice yourself. So the solution is cos x plus x times sine x. If you don't believe, you can quickly derive this to see that this is the original integral. So, and now we come to the third step. I hope I have enough space here. So the third step is to add the homogeneous plus the particular solution. Let's start with the homogeneous one, which is c times 1 over x plus the particular one. And you see the formula here, up here. So it is the constant we have already computed right now. Cosine x plus x times sine x times the e power minus ax function, which is in our case 1 over x. So we have already computed it. It's the same as from the homogeneous solution. Fine, so the only thing what remains is to figure out what is the constant c here, and you can get it from the initial conditions. If you incorporate the initial condition, you get this remaining constant. So what have we learned? We have learned that also first order linear differential equations with non-constant coefficients can be solved using the homogeneous and particular ansatz, as we have written down here in part 3. That's all. Thanks so much for your attention and see you soon.